Hey everybody. Today we're introducing groups. Groups are one of the most fundamental concepts in all of mathematics. And if you're studying the subject at all seriously, you're going to need a deep understanding of groups and their properties. So let's get started with the definition. A group is just a set with an operation. And the first example you should bear in mind is the integers with addition. For now, we'll call the operation star so that we aren't automatically thinking of addition or multiplication or any other specific operation that we already know. That operation has to have a few simple properties. First of all, if you have two elements in the set, call them A and B, then A star B also has to be in the set. For shorthand, we say that the group has to be closed under its operation. For instance, if we add any two integers, we get a third integer back. So the integers are closed under addition. Secondly, there has to be an identity element in the group. An element so that, let's call that element E, so that E star A and A star E are both equal to A. In other words, the identity element doesn't do anything when you apply it to any other element in the group. When we're talking about addition with integers, the identity is going to be the number 0. 0 plus any number is just that number again. Third, every element in your set has to have an inverse. So if the element is A, you have to have a number such that A star A inverse is the same as A inverse star A is the identity element. When we're talking about the integers with addition, the inverse of any number is going to be its negative. Finally, the operation has to be associative. If you have three elements in the set and you want to do A star B star C, it doesn't matter which of those stars you apply first. Groups really are everywhere, and by the time you're ready to see this video, you will have already encountered dozens of them. Let's run through a few examples. First of all, I already mentioned the integers with the operation of addition, where the identity is 0 and the inverse of each number is just its negative. The non-zero rational numbers, call the set Q star, with the operation of multiplication. Now the identity is 1. 1 times any rational number is that same rational number. And the inverse of each number is its reciprocal. You can see why we had to leave out the value 0. 0 would not have an inverse, and so if we kept it in the set, we would no longer have a group. Permutations of a finite ordered set. Let's call that ordered set A1 up to AN, where the operation is composition. So if we compose two permutations of this set, we get another permutation back. Do the first permutation, then do the second. Every permutation is going to have an inverse. Just undo the permutation. There is an identity permutation that's going to map A1 to A1, A2 to A2, and so on. The set of all polynomials where the operation is addition. If you add any two polynomials, you get another polynomial back. The identity element will be the 0 polynomial, and the inverse of any element is just going to be its negative. Finally, the set of all transformations of Euclidean 3-space that preserve distance between points, so-called isometries. So here again, the operation will be composition. The identity will be the transformation that doesn't move any points at all. The inverse of a transformation is just going to be the transformation that moves the points back, and so on. Here's a few examples of sets with operations that do not constitute groups. The integer z with the operation of multiplication. Most elements here don't have inverses in the set. For example, the inverse of 4 would be 1/4, and 1/4 is not an integer. The positive real numbers, x greater than 0, with the operation of addition. There's no identity element, no element e such that x plus e equals x for all x in the set. Here we would like the identity element to be 0, but of course 0 is not in the set. So the identity element does have to lie in the set. The set of all vectors in R3 with the operation of the dot product. Here we have a set and an operation, but the operation is, or rather the set is not going to be closed under the operation. If I take the dot product of two vectors in R3, I'm not going to get another vector in R3 back. I'm going to get just a real number. To summarize, a group has to map any two elements of the set to another element of the set. There has to be an identity, and there must be inverses. And of course, the operation has to be associative. Notice that I haven't been proving associativity in each one of these cases. It's a little more tedious to do so here and elsewhere. Here's another example. The collection of all real n by n matrices with non-zero determinants is going to be a group, usually called GLR, under the operation of matrix multiplication. By the way, the GL stands for general linear group. So the product of any two n by n matrices is another n by n matrix, and if each of the individual matrices are invertible, so is the product. One way to see that is that the determinant is multiplicative. The determinant of AB is the determinant of A times the determinant of B, where A and B are both n by n matrices. So if both A and B have non-zero determinants, so does their product. Matrix multiplication is associative, and matrices with non-zero determinants are invertible, things that we know from linear algebra. There is an identity element, just the n by n identity matrix, that has ones on the diagonal and zeros everywhere else. One thing to notice here, if you have two n by n matrices, the product, when you're doing the product, order almost always matters. AB in general is not equal to BA for elements of GLRN. So when you're talking about groups, there's no requirement that the operation be commutative. If the operation is commutative, we say that the group is abelian. We don't generally say it's a commutative group. We tend to call it abelian. Most groups that you'll encounter are non-abelian, and so you should never assume that A star B is B star A unless you have good reason to know that. Frequently, groups are well understood as collections of symmetries, as in this next example. This is an extremely important and common example. You should bear it in mind. Here's an equilateral triangle with the vertices labeled A, B, and C. Let's let the set S3 be the collection of all symmetries of that equilateral triangle. We can rotate this triangle 120 degrees in either direction. That's a symmetry. Those are symmetries. Or we can reflect it over any of the three lines that cut the figure in half. That'll pass through one of the vertices and the center of the triangle. So let's be a little bit more specific. Let's start with the symmetry that rotates this figure 120 degrees counterclockwise. Let's call this R1. So the vertex A becomes the vertex B, the vertex C becomes the vertex A, and the vertex B becomes the vertex C. Let R2 be a counterclockwise rotation by 240 degrees, like I've pictured here. Of course, that's just the same as rotating 120 degrees clockwise. Finally, we can get an identity transformation, an identity symmetry, by rotating by 0 degrees, or 360 degrees, for example. We also have three reflections, three reflective symmetries. We can reflect over the line that passes through A and that is orthogonal to the side connecting B and C, for instance. Let's call that one S3. We'll let S1 and S2 be defined similarly. So we have 6 symmetries: E, R1, and R2. Those are all the rotations, including the identity transformation that rotates by 0 degrees. S1, S2, and S3, the 3 reflective symmetries. Now, if we compose any 2 of those, we get a symmetry back. For instance, let's do R1 first, and then S2. S2 composed with R1. First, we do a counterclockwise rotation by 120 degrees. That moves A from the top to the lower left, and so on. And then we do a reflection over the line that I have pictured here. That reflection is going to flip A and B and keep C the same. Notice that this composition, S2 composed with R1, gives us the same transformation as S3. It fixes the vertex A and reverses B and C. So we've determined that S2 composed with R1 is S3. So if we compose two elements in this set, we get another element back. In fact, if we compose any two symmetries, we get another symmetry back. And so with a little effort, we can actually construct a sort of multiplication table. So here the first symmetry is written on the top line, and then the second symmetry that you apply is written on the left. If you apply the column symmetry first and the row symmetry second, you get the corresponding symmetry back from this table. With a little bit of inspection here, we can see that if we compose any two rotations, we get another rotation back, including the identity transformation in our rotations. If we compose a reflection and a rotation, we get another reflection. And if we compose two reflections, we get a rotation. Together, taking all of this together, we can see that S3 with the operation of composition is a group. The composition of any two symmetries is again a symmetry. There's an identity element, E, namely the rotation by 0 degrees. Every symmetry has an inverse. For instance, R1 and R2 are inverses of one another, rotating by 120 degrees and rotating by 240 degrees. No matter which order you compose those, you get the identity rotation by 0 degrees. Finally, composition of these symmetries is associative, as you can check by hand. Let's also point out here that this group is non-abelian. Order does matter in many, many cases. S1 composed with S3, for example, is not the same as S3 composed with S1. Finally, one other important piece of terminology. The order of a finite group is just going to be the number of elements in the set. For instance, S3 has 6 elements, and so we say it has order 6. Okay, so that's just a super quick introduction to groups. Keep an eye out for them as you continue to study math. You will find them everywhere.